Hi, my name's Paul Scott Murphy and I'm the Chief Technology Officer at WANdisco. We work with automotive manufacturers and suppliers to solve some of the challenges that come from the data generated by connected vehicles, and think some of what we've learnt is really important to the goals of SOAFEE. So I want to talk to you today about the implications and challenges that emerge from building these types of things, and explain how some of WANdisco's automotive customers are taking advantage of the opportunities that come from the availability of rich data sets that SOAFEE implementations help generate. We really believe SOAFEE has the opportunity to provide capabilities for data transfer technologies that can't be achieved at the application level, and I wanted to explain to you why that's important. So let's get straight into it. Let's start by looking at the fundamentals of data challenges at scale. What's driving that? And in particular, the most fundamental aspects of whether and where it's possible to use all of the rich data that connected vehicles generate. Transferring data off vehicle is going to require bandwidth. So let's look at those fundamentals. How much data will be created? How much bandwidth exists in cloud service providers to consume that data, to process it in the aggregate? Now, current cloud service provider interconnect capacity per Equinix's Global Interconnect report is roughly 2 petabits a second, or about 8 zettabytes a year. That's predicted to grow by a factor of about 2 within 2 years' time, allowing cloud providers to support data transfer rates that total just under 4 petabits per second. Now that may sound like a lot, and it is, but you're busy building generators of much larger quantities of data. The sensors in a typical connected vehicle are estimated by Intel to generate about 4 terabytes of vehicle data per day. And of course, depending on how successful you are with your implementations, the total data volumes that result are likely to far exceed the capacity of cloud service providers to be delivered those data sets. The low end, we're talking roughly 15 zettabytes a year. The high end, if we've achieved global saturation of connected vehicles with 1 odd billion vehicles a year, we're talking many, many thousands of multiples of the available cloud interconnect capacity to service those data transfer volumes. So my first proposition is that there's a data gap. The success of SOAFEE and connected vehicles in general is going to create a need for the better use of available bandwidth. The gap between the volume of data generated by connected vehicles and the capacity to transfer those data sets out of vehicle is growing. That implies more local processing of data for storage, compression, filtering, and aggregation in vehicle, justifying SOAFEE's technical vision for providing an automotive central compute solution architecture, but also more local storage, right? Potentially out of scope for a cloud-native architecture for a mixed critical automotive system, but definitely required for the operations of those systems and the data that they generate. So my second proposition is what emerges from the data gap, that automotive data require edge storage. Most of the data transferred from connected vehicles will be stored in vehicle first, and that's just a result of the overwhelming volume of data generated by sensors in vehicles. Now, this implies SOAFEE can benefit from some shared intelligence about data transfer requirements. The key optimizations that can be achieved can bridge the data gap, but they require knowledge and use of systems and services that are external to the containerized runtimes of independently created mixed critical systems that SOAFEE enables. So I want to talk to you about that potential need to look at the data generated by SOAFEE implementations and how that impacts the fundamental requirements of large-scale data transfer requirements for connected vehicle solutions. Now let's look at autonomous vehicle data. The type of inbound bulk data transfer flows that occur are very similar to a typical edge-to-cloud scenario, where at the edge you've got sensors and IoT devices, right? In vehicle, it's your radar, LiDAR, other devices, data acquisition systems, capturing the outputs of those sensors, some form of edge computing, whether that's for processing or storage, right? And then the transfer from edge to cloud of data sets, where vendors like WANdisco and other technologies play a role, and then the target environments for those data sets, whether that's public cloud or private cloud implementations. But there is an aspect of delivery of those data sets to non-vehicle environments for processing, storage, subsequent use in the aggregate. When we're talking data transfer, there's really 3 broad approaches that exist for it. Application specific, where applications themselves are modified with explicit knowledge of the need to transfer data and perform that work. typically used in vehicle-to-vehicle communications, vehicle-to-X messaging, custom data transfer solutions from sensor events to shared storage elsewhere. Obviously highly configurable, highly custom, expensive to implement. Second broad approach, file system transfer, where data generated in vehicle are stored in vehicle or stored in near edge environments of vehicle, where data transfer of selected sets of file system content can occur, treating those file system storage services as an element of the edge environment, performing edge to cloud transfer, relying on some technology to do that work, delivering that to the target environment where data are processed or stored in the aggregate. Third broad approach, volume-based replication, where the underlying storage infrastructure in vehicle is replicated as a whole, all or nothing, to some target environment. Now that typically requires some coordination between the in-vehicle storage and the target environment, relying on the storage services at each end of that data generation and destination, being aware and capable of that volume-based replication. Perhaps less advisable for the type of solutions required for connected vehicles. So with those three broad approaches, let's look at the common requirements that underlie data transfer at scale. These are what WANdisco has learned is unavoidable. And I would posit there are really 8 fundamental requirements for very large-scale data transfer: security, high speed, fault tolerance, scalability, manageability, automation, flexibility, and the ability to work in a distributed manner. I wanted to detail a little bit more about the aspects of each of these that are important for connected vehicle implementations. Security, an obvious first place to start. One of the elements around security when you're dealing with that in terms of data transfer is that security goes beyond the boundaries of the vehicle itself and needs to take into account the capabilities and services of the target environment. So the cloud native data security and data transfer requirements for connected vehicles needs to understand and leverage the full capabilities offered from cloud native storage services, the APIs, the interfaces to secure data transmission, but also the ability to define and control authentication and authorization against data access in that target environment. Cloud storage services provide different capabilities to local storage in vehicle, and a data transfer solution needs to understand and take advantage of that to ensure the end-to-end security of data. High speed is the second key data transfer requirement, another clearly obvious one. The speed of transfer, though, can be business critical for the monetization of the data sets generated from vehicle environments. So it needs to be capable of consuming available bandwidth when needed. And that means an understanding not just of network capacity, but of the potential and optimal use of all of the available time for data transfer. So data transfer solutions that can benefit from using time in a better way to meet business goals are better able to service the needs of data transfer speeds effectively to monetize the data sets. Third key requirement around large-scale data transfer is the fault-tolerant nature of this. Now, it's been said the future is not evenly distributed. Connected vehicles, I would argue, are an extreme example of that, with very adverse network conditions, ensuring that data bandwidth for transfer is not available at all times. But even the cloud services to which data transfer might need to occur can vary in their own capacity, their reliability, their functionality, and even their security by location, with different jurisdictions providing different levels of service around all of these aspects. Data transfer solutions need to take these into account in their implementation. Scalability is another key requirement. Elements of scalability can be non-intuitive, though. You need to think about scalability not just in terms of the data volumes themselves, but it's scalability in terms of time, again, taking advantage of available time. Scalability in terms of the network links available, taking advantage of physical infrastructure that changes over time, particularly in connected vehicle implementations. The service limits, too, of the target environments to which data transfer occurs will change over time. The scalability of solutions to accommodate that needs to have an understanding of that in the aggregate to be able to work effectively. So data transfer solutions need to accommodate those aspects around scalability as well. A fifth point to note around data transfer requirements at large scale is the manageability of this. It's very difficult to implement point solutions at the application level that can accommodate overall management of data transfer requirements without being impeded or constrained or restricted by their peer applications in vehicle. And that really requires externalizing data transfer from the automotive systems that generate data. So that edge to cloud depiction of sensor devices, acquisition, storage and processing, and then transfer is a fundamental requirement around making it manageable at scale. This also allows, though, independent development and enhancement of the systems that generate data, better accommodates changing external environments by separating that from the applications generating data, and can benefit from shared intelligence about external capacity and changing constraints for data transfer. Automation, really key again for large-scale data transfer. That's not just about the ease of operating data transfer solutions, but about eliminating disruptions to source systems to avoid the need to implement answers to that in the generators of data sets again. Also to minimize the impact of implementing data transfer in vehicle, things like reducing the power draw on storage subsystems, which can occur for solutions that attempt to repeatedly scan a data source to identify what's changed to initiate data transfer. You need a more intelligent approach to doing that. It can also accommodate, automation needs to accommodate changing and variable data volumes without impacting either the operators or users of the vehicles or the infrastructure on which they rely. So automation, again, key at large scale and very challenging. Second last one, flexibility. Abstractions of storage services can really help SOAFEE implementations support a more flexible approach for data transfer by providing common approaches at the level of hierarchical file storage, perhaps present on in-vehicle or in near-edge environments. It's better able to perform data transfer, or solutions better able to perform data transfer that can map readily between those storage services at the edge and the target cloud storage services to which data need to be transferred. Different storage services in the cloud have different capabilities. You really need a solution that's flexible and capable of both avoiding modification of container workloads just to support the dynamic delivery of content to either one or multiple destinations that are going to change over time. So flexibility is really important in thinking about large-scale data transfer requirements. The last fundamental requirement I want to touch on before we summarize the presentation is to think about the distributed nature of data transfer at scale. The complexity that emerges from the dynamic allocation of network, storage capacity, the changing rates of data generated over time, make this a very difficult thing to automate and manage at scale. So the distributed nature of the source data set generators contributes to this very heavily. Answers to how that can be accommodated need to be cost model driven. So having inputs that relate to the cost of both servicing data transfer requirements, but also the opportunity cost of avoiding the business outcomes that are being targeted by reducing data transfer at times, can play a role in optimizing the overall benefits that come through data transfer. So aim for solutions that support cost model optimizations rather than fixed outcomes. They have to accommodate changing environments, whether that's technical, physical, or business requirements changing over time. By leveraging information and control over network capacity, calendaring information, bandwidth calendaring, and the like, some benefits can emerge that are better served at the platform level rather than at the application level in vehicle. So data transfer, taking advantage of those 8 fundamental requirements, data transfer solutions, is going to better service the needs of autonomous vehicle data transfer in general. So let's summarize that very briefly. Large-scale data transfer, very fundamental to connected vehicles. Data volume is obviously significant per vehicle, but obviously in the aggregate. Streaming data and bulk data will coexist in connected vehicle solutions, but bulk data will constitute the majority of data volumes. The data gap that exists because the generation of data far outstrips the capacity of network infrastructure to consume those data sets means that solutions are required at the platform level to implement data storage in vehicle and to incorporate cost-based optimizations for transfer that take into account all of those fundamental requirements for large-scale bulk data transfer. We walked through them all. Security, speed, fault tolerance, scalability, manageability, automation, flexibility, and the distributed nature of connected vehicle solutions. So thanks very much for listening to my presentation today. I'm very pleased again to give you some insight into what WANdisco has learned in implementing connected vehicle data transfer solutions for some of our many customers. Again, thanks very much.